Hi, welcome to this module. In the last module, if you remember, I said that we will see actuators in the next class, but before moving to actuators, let us see what kind of sensors we have and what are the roles of those sensors in real life and in the biomedical space. Okay, we will talk about lot of sensors related to healthcare technologies, because that is where I particularly focus in, and I feel that it will be very interesting for you to understand how getting knowledge of fabrication of microsensors and actuators will help you to design a technology that can be used in healthcare domain as well as in different applications. So, having said that, this was the last slide in the class that I talked about, that how the physical principles of sensing and sensor types are related, starting from charges and application was from Seebeck to filter effects to heat transfer and light, and further we discuss about the direct and indirect kind of sensors. Now, sensors, when you talk about sensors, sensors are fabricated using a material called silicon, right. So, any substrate, actually what is substrate? If I say substrate, what we mean by substrate, alright. So, substrate is any material on which we are going to fabricate a sensor or an actuator, alright. This is very easy definition of a substrate, a material on which we are going to fabricate our device, that becomes a substrate. Okay. Now, this material can be glass, so glass can be used as substrate, this can be silicon, right, this can be germanium, this can be an insulating material, already we have discussed, this can be a metal as well, this can be polymer as well, all right. So, substrates when we define, it can be a material made up of polymer, semiconductor, polymer will be an insulator or a conductor on which we are going to fabricate a sensor, all right. Now, in this particular space, 90% of the sensors are fabricated on silicon, So, silicon is a semiconductor, right, you should know. Some of the basic prerequisites are required for understanding this particular course, right. For example, if I talk about intrinsic or extrinsic semiconductors, right. What do you mean by intrinsic semiconductor and what do you mean by extrinsic semiconductor, right. So, this is what I expect that you should know, right. People who do not know, for them I am just giving you definition of intrinsic and extrinsic. Intrinsic is where the material is not doped with any kind of impurity, that is how we say it is a intrinsic kind of material. When you dope a silicon wafer with any dopant like N type dopant or a P type dopant, then we say it becomes an extrinsic kind of material, alright. So, when you dope a silicon wafer with pentavalent impurities, it becomes N type. When you dope a silicon wafer with trivalent impurities, it becomes P type, right. And then types of wafers that you can identify, it is 100 orientation, it is 111 orientation, it is 110 orientation. Is it N type or P type? So, N type 110, P type 110, N type 111, P type 111, N type 100 and P type 100. These are the classes. How? So, if I give you a wafer, can you identify whether the wafer is n type or whether the wafer is p type, and if the wafer is n type, then within n type which orientation the wafer has. So, that we can understand with the help of Miller indices or Miller index. So, I expect that you understand Miller indices, I expect that you understand the types of silicon wafer, and then from that knowledge we are going to talk further about how to fabricate sensors and actuators. Alright. So, silicon, when you talk about silicon, in specially silicon is fabricated using what? Silicon is fabricated using sand. And what is sand? Sand is nothing but silicon dioxide, SiO2. Right. So, 99.9% pure sand is used, right, and there are two processes. This is again within the prerequisite. There are two processes, one is Czochralski technique and one is float zone technique, through which the silicon dioxide is processed and we have a silicon wafer to work on. All right. So, and the final wafer that we have is pure, has a purity of 99.9 times 9, 1, 2, 3, 4, 5, 6, 7, 8 and 9. This is the purity of the silicon wafer that we are looking at from the silicon dioxide, which is 99.9% pure. Right. So, there are silicon foundries which fabricate the silicon wafer from the silicon dioxide material. Alright. So, when we talk about silicon, you will see that silicon bowl is there from which the wafers are sliced, and the bowls are nothing but the large logs of silicon, right, and then these logs are sliced to form the uniform silicon wafers. Right. So, how and where would this silicon bowls would be fabricated, or where the silicon wafers would be sliced and fabricated, all right, in what kind of environment it would be, right. So, that is our second part. So, when you talk about silicon bowl, right, you can see this particular picture, and looking at this picture, what do you think the, or where do you think the silicon balls are made, and why do you think so? Right. You can see that this person is wearing, the technician is wearing, or engineer is wearing the gown, right, and it is a foundry, but what kind of environment is there? So, this is a clean room environment, okay, and then within the clean room there are several classes of clean room. If I say clean room, then there are several classes of clean room, right, starting from class 1 to 10 to 100 to 1000 to 10,000, right, to 100,000. So, these are several classes of clean room, and depending on what kind of fabrication of sensors or actuators we are going to see, we can use that particular class of clean room. For our experiments, we will be focusing more on class 1000 and 10,000 kind of clean room, where you want to go for foundry, you have to go for class 100 kind of clean room, right. Sometimes you can also go for class 10 kind of clean room. Okay. So, now we identify that, okay, this fabrication of bowl should be in a clean room environment, all right. But the second question is, why we think so? The requirement of the clean room is to avoid any impurities. So, if the more the room, the class, if it is 1 or 10 or 100, the room is much more cleaner, and less of the impurities are present in the room compared to room which are not clean. And we want our silicon wafer to be not doped with impurities, isn't it? Because even one small single impurity of 0.5 micron will kill your entire chip, right, because now we are talking about few nanometers of technology, where you are going to fabricate MOSFETs, and if you see the technology to fabricate metal oxide semiconductor field effect transistors, it is a few nanometer technology. So, in terms of few nanometers technology, if there is a 0.5 micron particle that sits on the wafer, it will kill thousands of transistors at the same time, right. So, to avoid that, we require to have a clean room facility. Okay. Now, if you talk about fabrication of the silicon wafer, right, then this is how the silicon wafer is fabricated. There is a video which you can go to YouTube and you can see how exactly this silicon wafer is fabricated, but it starts with the crystal growth and seed crystal. This is a seed holder, and then there is a seed crystal which is inserted into the silicon melt, right, and these are polysilicons which are heated at a high temperature, so that it becomes a melt, and then this rod is inserted and it is pulled out slowly in a uniform fashion, such that you start forming the single crystal silicon. All right. This the system consists of a crucible shaft. The direction of this shaft is opposite to the direction of the rotation. The rotation of this particular crucible shaft is in opposite direction to the rotation of the seed holder, as you can see here, right. This is a opposite rotation compared to this one. Second thing is that there is a silicon melt, as you have seen. There is a crucible susceptor, and then there is a heater, right. See, there is a heater that will heat this material, and that is a material in which or the chamber in which the silicon melt is holded or polysilicon is holded is a crucible, is called crucible, and there is a crucible susceptor, right. And as you can see, this is a silicon melt, right. This one is silicon melt. Now, finally, you have to cover this with a thermal shield, and that is why you can see here there is a thermal shield covering the entire system, right. And when you pull out the silicon seed, slowly this is at lower temperature compared to this one, and that is why you start forming the single crystal silicon. So, it starts with these are the steps. It starts with the melting of polysilicon. This is step number 1, right, and then there is the introduction of seed crystal, step number 2, following by beginning of crystal growth, step number 3, then the seed crystal is pulled out, and then there is a crystal pulling and formation of the silicon bowl, step number 4, and finally the crystal is formed, step number 5, right. So, this is how the process is done. Like I said, there are two techniques, Czochralski technique and float zone technique. You have to go to any VLSI book, you will find it out, and that is how we finally end up in having a silicon wafer. Of course, there is a slicing required and many more things are required. Before we understand that particular process, now let us see that what kind of sensors we are going to study in this particular course. I am giving you a few examples, right. That does not mean that we are only going to study this few, but we will study in detail how to fabricate those sensors. All right, and what are the application of those sensors. That is our understanding and our idea to understand this particular course. So, if you see the first one is a micro heater, right. So, if I say what exactly this particular micro heater is, then what I can show it to you, that what do you mean by heater and where the application of the heater would be. So, if you see this particular slide, right, what is this slide showing? Micro heaters. But first thing is, why we require a micro heater? Why? Second question is, how we are going to fabricate this micro heater, right? How we can decide the resistance of the micro heater, right? And third question is, what are the processes involved? Processes involved. Why you want to fabricate a heater? For fabricating of a heater is used in many applications, in sensors, in microfluidics, in medical applications, as well as in understanding electronic nose. I will discuss with you what exactly electronic nose means, and if you want to fabricate this heater, why it is called micro? Because the width of this particular line that is forming the heater, right, is of few microns. As you can see, this is a 3 millimeter here the bar. So, this is close to about 100 microns, the width is 100 microns. Alright. So, I first of all how you are going to design a heater such that for a particular resistance. What I mean by particular resistance? Suppose I say that I want a resistor which is of 120 ohms. Okay. Now, this is what, this is the heater resistor, heater resistance, right. If I have a heater, it should have a resistance because it is nothing but a metal coil, right, it is a coil. So, I should have a heater resistance. Now, how can we get 120 ohms of resistance, right. So, first thing is what kind of metal you will be using, right, whether the metal is platinum or metal is polysilicon, or you are going to use polysilicon instead of metal, or you are going to use nickel, or you are going to use nichrome, right. Now, why we are discussing about this particular metals? We are discussing these metals because the resistivity of each metal would be different, right. The resistivity of each metal would be different. So, say that you select one particular metal, and let us say we are selecting nichrome, all right. So, my resistivity is constant, right, because I am not going to change the metal. What else forms the resistance? So, if I ask you the definition of, or I write down the equation of a resistor, what is the equation of resistor? Most of people will answer, oh, it is V equals to I R, and that is why R will be equals to V by I, right. But that is not a correct answer. This is okay, this is not right, really wrong, but this is what you are saying is a Ohm's law, and how resistance depends on voltage, ratio of voltage and current. I am not talking about how the resistance is depending on voltage and current. I am talking about how you are going to form a resistor of a particular value, and that is why this equation will not hold true for a resistor. So, for resistor our equation would be rho into length by area, correct. So, I now know what is the resistivity because I have selected a particular material. So, I know the resistivity value, right. Length I can play with, and so is the area, right. So, I will decide the number of turns and the area that a heater will cover, and depending on that I will have a resistor value. Now, what is area? Is nothing but R I can write. So, this will further, if I further the equation will give us R equals to rho L by W into T, where T is your thickness, W is your width, correct. So, now my resistor will depend on the length of the coil, the width of the coil, width of each line, and the thickness of the material, correct. So, by calculating here we can form a resistor of a particular value. You got it? Easy, extremely easy, right? Okay. Now, what does it mean? That means that if I increase the length, my resistance will increase. If I increase the length, my resistance will increase. If I decrease the length, resistance would decrease. If I increase my area, my resistance would decrease. If I decrease my area, resistance would increase, right. Thus, my resistivity remains constant for a given temperature. My resistivity will remain constant, right. So, from here we can design a resistor of a particular value. right. Thus, the different designs that you see here, right, are based on the resistance that I want. And what is this green color thing? You must have guessed that this is nothing but a silicon wafer, right. This is a silicon wafer, but why silicon wafer is this green and purplish color, right. So, let us understand. Okay. I said that why you require heater. Heater is used, why you require heater? Heater is used for several application, including ENOS, microfluidics, ENOS, right, which is electronic nose. I will discuss with this particular topic in detail, microfluidics. Then we require heater for each individual metal oxide semiconductor based sensors. Okay. So, there are a huge application of the heaters in this particular domain, but also micro heater is required for other applications. For example, if you want to have a smart actuator where you want to heat and cool the system, right, in real time. So, for heating there you require a micro heater, right. So, there is a lot of application of why to use the micro heater, why to understand the micro heater is a part of this course, right. But the second point was that how we are going to fabricate this micro heater, right, and at least we understand right now is that we can design the resistance of the heater with the help of its equation, right. Now, the third point is how you are going to fabricate this particular. So, what are the processes, right, what are the processes involved in fabricating this particular heater. So, the processes that are involved in fabricating the heater are called micro fabrication technologies, micro fabrication technologies. Okay. So, in microfabrication technologies there are several things that we will be learning, starting from the silicon wafer, which is our substrate, and then on the substrate we have to. So, if I have a silicon wafer, that was my earlier thing that I wanted to teach you. There is a silicon wafer, right. Now, if I deposit a metal on silicon wafer, this is a metal, this metal is, let us say we have selected nichrome, right, we have selected nichrome. So, if I pattern this nichrome using a microfabrication technology, then I will have this particular heater, this silicon, and this is my nichrome heater. All right. Will it work like whatever we have understood till now about the heaters? Will it work properly? Yes or no? If I directly deposit a metal on a semiconductor, right, and I fabricate a heater and I ask a question, will it work properly or not? What is the answer? No, right. We require a insulating material between the silicon wafer and a metal, since silicon is a semiconductor. If I cannot directly deposit metal on semiconductor, otherwise I cannot follow or have the parameters of the heater and the working of the heater in the same manner that I have decided. So, what I will do? I will grow a insulating layer as a sandwich between my metal and a silicon wafer. So, what does that mean, right? What I mean is, you take a silicon wafer, right, and then you grow silicon dioxide. This is silicon wafer, this is silicon dioxide. Silicon dioxide is an insulator, right. On this you deposit your metal, which is your nichrome, and then you fabricate your heater, silicon dioxide, silicon and you have your heater here, right. I will teach you, okay, how to fabricate this heater. Right now you just assume that you have patterned this heater, and this is the correct way of fabricating a micro heater. So, here what we have learned? We have learned that you require a silicon wafer, right. Then you need to clean the silicon wafer. So, cleaning process is what several processes I told you. What kind of processes are involved? The process for fabricating the heater requires a silicon wafer which needs to be cleaned, right, and followed by you have to grow silicon dioxide. So, silicon dioxide we have to grow using thermal oxidation. Thermal oxidation. You may have studied, if you are from electronics background, you may have studied how the MOSFET is fabricated, right. MOSFET. In MOSFET there is a gate oxide, right, thin layer of gate oxide, and then there is a filled oxide. The gate oxide is formed with the help of thermal oxidation process, right, and that is a dry oxidation, while the filled oxide, which is thicker, is formed using a thermal oxidation process, but wet oxidation. So, dry oxidation, wet oxidation for filled oxide, dry oxidation for gate oxide, easy. So, for growing silicon dioxide, now what is the difference between dry oxide and gate oxide? Dry oxide is of higher purity compared to wet oxide, sorry, not dry oxide and gate oxide, dry oxide and wet oxide. Dry oxide is of higher quality compared to wet oxide, but wet oxide can grow faster compared to dry oxide. Why there is a higher quality? Because there is no hydrogen atoms involved in that. The wet oxidation is done with the help of water vapor, while dry oxidation is done only in oxygen. Okay. So, you have to clean the wafer, you have to grow silicon dioxide using thermal oxidation. Next step is what? You have to deposit a metal, right. So, deposition of a metal will require you to understand physical vapor deposition. Physical vapor deposition techniques. This stands for physical vapor deposition. All right, physical vapor deposition. This is for depositing nichrome, right. Now, in physical deposition techniques, there are several techniques that we will learn, right. I will teach you all these techniques when the lecture comes, right, and those techniques, three main techniques. One is called thermal evaporation, not oxidation, okay, thermal evaporation. Second is called electron beam evaporation, and third one is called sputtering. Thermal evaporation, electron beam evaporation, and sputtering. These three are physical vapor deposition techniques that we will be learning in our course. Right. After metal you deposit, right. From metal to fabricating this particular heater, this is a cross sectional view of a heater. What we require? We require to understand photolithography. Photolithography. Okay. And when you understand photolithography, photolithography is considered as a heart for any microfabrication technique. Once you understand photolithography and you use it on this particular wafer which has a metal and silicon dioxide, you can fabricate a micro heater. Alright, so these are the processes that are involved in fabrication of a micro heater. We will see process in detail, right, when we talk about that particular slide, right. So, this is a micro heater, and let us go to the next section, which is your interdigitated electrodes on silicon dioxide on micro heater. Right. So, what you can see here, you can see a micro heater, right, and then there are interdigitated electrodes on the micro heater, right. So, how you can fabricate this interdigitated electrodes on the micro heater. So, if I go back, right, what I have is a micro heater. So, I will just if I further it, I will have a micro heater, right. This is silicon dioxide, this is silicon, and this one is my nichrome micro heater. On this micro heater, what I want is interdigitated electrodes, but if I directly deposit metal on this, is it correct? No, right, because heater is also made up of metal, and my interdigitated electrodes will also be fabricated using metal, chrome gold, right. So, what should I do? I cannot put one metal on second metal, otherwise it will be shorted, right. That is why I had to again deposit silicon dioxide as a sandwich layer between my heater, and then on this I will deposit a metal, which is my chrome gold. Alright. Why use I had to use thin layer of chrome to improve the adhesion of gold. The adhesion 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 of gold on the oxide is poor, and to improve the adhesion we use a thin layer of chromium. Okay. That is the role of chromium, that is why always we say chrome gold. So, when we deposit chrome gold on the heater, we have to make sure that there is a silicon dioxide or an insulating layer between the heater and the interdigitated electrodes. After depositing chrome gold, I will perform a photolithography, so that I will have my interdigitated electrodes. Got it? So, I have my interdigitated electrodes made up of chrome gold. This process we will learn, and that is how it looks like, that there is a interdigitated electrodes, right, over silicon dioxide. You can see here that silicon dioxide is a sandwich layer between micro heater and interdigitated electrodes, right. And then below silicon dioxide there is a micro heater, which you can see here, right. So, this is how the SEM image looks like. SEM stands for what? Scanning electron microscopy, scanning electron microscopy, SEM. Okay. So, these are all, this one, these are all SEM images of interdigitated electrodes on silicon dioxide on the micro heater. Alright guys, easy. So, let us move to the next one. So, lot of sensors. Okay. We will be talking about very important application during our course, which is on atrial fibrillation. And why we are talking about atrial fibrillation? Because we want to understand how we can fabricate a sensor which can measure the force in real time. Okay, we can measure the force in real time during the surgery, So, what exactly atrial fibrillation means, we will discuss in detail in the one of the classes. For now, let us understand that atrial we all know, right, our heart pumps uniformly. Everybody has a heart, everybody has a heart, right, okay, and it pumps, otherwise we will be dead. It pumps a certain number of beats per minute, isn't it, right. Now the question is, if it pumps faster, what will happen? If it pumps slower, what will happen? If it pumps uniformly, then what will, or non uniformly, then not sorry, my mistake, non uniformly, then what will happen, right. So, generally when you run, heart beats faster, right, you are waiting for your exam results, your heart beat faster, but that is fine, because it gains back its normal rhythm as soon as you are less stressed or you stop running and you are at your standing position, suddenly it comes back to its normal rhythm. But in a disease called arrhythmia, this pumping is very fast, it does not come to normal rhythm without taking medicines. And in one other application, other disease within that arrhythmia is called atrial fibrillation, where your heart starts pumping unevenly. Now, when it starts pumping unevenly, it causes clots. Okay. So, how it is treated? This pumping unevenly is because of the misfiring of signals. You have to understand the physiology of heart, then you will understand how the heart works, and then you will understand there are electrical signals or pulses that are fired for the uniform pumping of your heart. That uniformity is lost because of the misfiring of signals, and we can restore that uniformity by burning that particular tissue which is causing misfiring of signal. How it is burned? So, the surgeon will put a tool called or a tube called catheter which on that particular tissue, and the surgeon will burn that particular tissue. I will teach you in detail how that is the process is done. Right now just understand what I am saying. Now, when I am saying directly like this, it does not happen like this, it goes from the groin area all the way to your heart and then it is posted. I am just showing you an example. Okay. So, now let us understand this is a heart and the tube is inside, this is your catheter, and to burn the tissue. Burning is called ablation, catheter ablation. Use RF energy, RF ablation, right. So, catheter ablation, RF energy, RF ablation. How much force you apply on the tissue, on the heart tissue is extremely important. More force if I apply, suppose I say that, if I can show it to you in a way so that you understand. Okay. Let us understand this thing. Okay. Can you see on my heart please? Yeah. Let us understand that this is the area which I want to heat, which I want to burn. When I apply force, if my force is more, then the other areas of the heart would burn, and that is I do not want. It should not happen like this, right. If my force is less, then what will happen? The recurrence will be higher. A subject, so a patient will feel that again their disease has the disease is not cured properly, and he or she will feel the non-uniform pumping of heart, right, after few days of the surgery. So, less force is not okay, more force is not okay. Optimized force is what we are looking at, right, and how we can apply an optimized force to the catheter. That means we need to have a force sensor integrated onto the catheter that can measure the real time contact force. How to fabricate this force sensor will be the objective, one of the objectives of our course. All right. So, I'll discuss this thing in detail in the one of the course. Let us go to the next topic, and here if you see the slide, we are interested in understanding the change in mechanical properties of the breast tissue course. All right. So, if you know that breast cancer is the second largest cause of cancer related death in women, okay, and when there is a tissue related cancer, the tissue properties are will change. A lump would be more stiffer or less stiffer compared to other parts, other tissues. So, the stiffness of the lump would be different. Now, if I give you a slice of a tissue and ask you to understand or tell me what is the elasticity of the tissue, what is the mechanical property of the tissue, or you can you measure the stiffness of the tissue, then there is a way to measure it, and that is by using a microfabricated micro cantilever. So, what I mean by a microfabricated micro cantilever, when I say micro cantilever, it is assumed that we use microfabrication. What is a cantilever? Can you give me an example of a cantilever? A simple example of a cantilever. A simple example of a cantilever would be a diving board, right. So, if you are seen in a swimming pool, a diving board is where a person will dive into the pool, but before that it is holded at one end and it can move at another end. This is a cantilever. Even simpler example, if you take a ruler or a scale and place it on a bench, right, then if I press it, it will vibrate like this, correct. This is a cantilever. Okay. So, there are example the poles, the night lamps, night poles in the street, light poles, right, there are also cantilevers. So, many examples, but now I want to fabricate a cantilever which is of micron size, and I want to embed a piezoresistive sensor onto the or into the micro cantilever. How can I fabricate a micro cantilever with a piezoresistive sensor? I will teach you. Now, right now let us assume that there is a piezoresistor embedded in this particular micro cantilever. What is piezoresistor? I am assuming that you know these terms, okay. Piezoresistor, piezoelectric, Ohm's law, Miller indices, silicon, everything, okay, intrinsic, extrinsic. That is what I mean by prerequisite. So, still to help you, piezoresistor is when you apply a pressure or a force, you know force and pressure how they are related, you will see the change in resistance, right. So, now if there is a piezoresistor embedded into this particular cantilever and I am pressing this cantilever, what will happen? There will be generation of stress onto the cantilever beam. This stress will cause change in the piezoresistivity, and that is why I can see the change in resistance. Now, if I have a tissue and I am pressing the tissue with the cantilever, depending on the stiffness of the tissue, my cantilever will bend, right. How much it bends will cause change in the resistance of the piezoresistive cantilever, since the piezoresistive cantilever, since this micro cantilever has a piezoresistor embedded into it. So, if the tissue is stiffer, my cantilever will bend more and I will see more change in resistance. If my tissue is less stiff, I will see less bending in the cantilever. You got it? That is how it is related. So, we will see in one of the class how the piezoresistive cantilever works, right, and how can we fabricate it. Okay. So, there are many more sensors that we need to understand. for this particular module, let us understand this many sensors. For next module, I will show you few more sensors that we will be learning in our course, and then we will see what are the actuators and what kind of actuators we will be learning as a part of this particular course. And then later on we will start understanding what is PVD, what is a photolithography, and we will start fabricating each sensor, and when I say fabricating, we will see the process flow in the class, and then we will see how exactly a sensor looks like. I will ask one of my TA to take a lab class where you will be where you will know how the clean room looks like, what are the things inside the clean room, and how the devices can be seen, right, what are the microscopes, how you need to use the microscope, when you have a chip, how can you make the electronic system, so to understand different properties of a given material. We will discuss all the things in this particular course, right. For today, I think this is enough for you to get the glimpse of some of the sensors, and I will discuss few more in the next module, followed by the actuators. If you have any questions, feel free to ask us in the forum, right. Till then, you take care, and I will see you in the next module.